First thing I would do here on question 1, like it says, is to rewrite. So if you have multiple terms in the numerator and one single term in the denominator, you can split this up into separate fractions. So x over the square of x minus 15 over the square root of x is equal to the square root of x minus 15. Actually, I'm going to write this as x to the 1/2 and then 15x to the negative 1/2. And you can take the integral of each term separately. Integral of x to the 1/2 is x to the 3/2, and then you need to multiply by 2/3. And then integral here, so 30 is x to the positive 1/2. Now, pretty easy one here. Rather than taking the integral of the entire expression, you can take the integral of each term separately, like this. So here you're going to have negative 4x to the 3rd over 3 plus 7x squared minus 3x. Okay, so we want to find the cost function. We've been given dc dx. This is the derivative or the marginal cost. So if you want to undo a derivative, you use an integral. So you got to move the dx over here, and then you can integrate with respect to x. Integral of dc is just c. And over here, the integral of 1/50th x is 1/100th x squared plus 20x. Not to be confused, this is plus c, this is the constant of integration. I'm going to call this just cost, so we don't get confused. Okay, now there's a fixed cost of $3,000 for when x equals 0. So if we plug in a 0 for x and a $3,000 for cost, that's going to help us find the value of c. Now if x is 0, that term disappears. If x is 0, that term disappears. So the constant of integration is equal to c. So the cost function is 1/100th x squared plus 20x plus 3,000. Okay, there's two ways you can do question 4 here. You can use u substitution, and then we've got the dz right here, but we're missing a 4, so if I place a 4 there, I have to place a 1/4 in front of the integral. Now all the pieces are where they need to be. So just using the general power rule, you get this answer. That's option 1. Or you could simply, let me start again here, you could expand this binomial. 1 plus 4z squared is 1 plus 8z plus 16z squared. So you can expand the binomial using the FOIL property, and then you can just integrate each term separately. So you either have this, or you have that. Okay, here I would definitely use the u substitution, and generally you're going to let u equal an inside function, which is going to be this. So the problem is that it's -5. We have the x and the dx. We're supposed to have a 2, so I'm going to go ahead and pull this -5 out here and put a 2 in its place. And then you're going to have to divide by 2 out here to even it out. So we're going to have negative 5 halves times integral of du over u to the 4th. So I'm going to change this into u to the negative 4 du. And I'll just use the general power rule of integration. We're going to get negative 5 halves times u to the negative 3 divided by negative 3. Negative and a negative multiplied together will be positive, so those become positive. So it's 5 over 6 times u to the 3rd. So it's 5 over 6 times x squared plus 5 to the 3rd power plus c. Okay, question 6. This ends up being an integration by parts, and we're going to have to do integration by parts twice. Remember the guidelines for integration by parts is you choose u and dv. U should be something that's, when you take a derivative, you end up with a more simple form. dv should be something easy to integrate. So I'm going to have to actually do a little bit of a rewrite here. Instead of having that there, I'm going to move it up there to the top, e to the negative x. So u I'm going to let equal 3x squared, which means du is 6x dx. dv is going to be e to the negative x dx. When you integrate e to the negative x, you get negative e to the negative x. So the pattern for integration by parts, if you have something in the form of u dv, which we have, this is u, and that's dv, and the integral of that is u times v minus the integral of v du. That's the pattern for integration by parts. So we have u times v minus the integral of v du. So v has a negative sign, so I'm going to go ahead and pull that negative sign out front. And du has a 6, so I'm going to also pull that 6 out, and it becomes positive 6. And then we have e to the negative x times x dx. And now this is going to require another integration by parts. So I'm going to let u equal x, which means that du is equal to dx. dv I'm going to have be e to the negative x dx, which means that v is negative e to the negative x. So now I'm going to write this whole expression again here, but I'm going to expand out this integral using the integration by parts formula. So we have negative 3x squared over e to the x plus 6. Now I'm going to write the expansion of this using integration by parts. So we need u times v, so this is x over e to the x, which need a negative sign there, minus the integral of v. Now v has a negative sign, I'm going to pull that out front. So we have x, or e to the negative x, and then du is dx, so that becomes plus. Okay. So we have negative 3x squared over e to the x minus 6x over e to the x minus 6 over e to the x. We just distributed the 6 here and here, and the integral of e to the x is negative e to the negative x. question 7. This is a u substitution. So we got the dy, but we're missing a -7. So we can put a -7 right there, but we have to multiply by -1/7 out front. So we have -1/7 is the integral of e to the u du, which is equal to -1/7 e to the u. So that's -1/7 e to the -7y plus c. Okay, if we try u substitution here, so this could be u. We got the x dx. We're missing the 14, so we can place a 14 and then multiply by 1/14. So we have 1/14 times the integral of du over u. The integral of du over u is the natural log of the absolute value of u, and that's what we have here. So this is 1/14 times the natural log of the absolute value of u. So this is 1/14 times the natural log. Now u is 7x squared plus 9. That's always going to be a positive value, so we don't need the absolute values anymore. There we go. Okay. This is an application of the integral. We can find not only the area under a curve, but we can find the area between two curves. So this is parabola, this is a straight line. So what this may look like, we have a parabola, a straight line, we have some area we need to find between the two curves. We need to find the bounds of integration. Sometimes they're explicitly stated in the problem. In this case, they've given us two functions, and we're assuming they intersect, forming natural bounds of integration, so we need to find those bounds of integration. You can find where two graphs intersect by setting the two functions equal to each other. So x squared plus 12x plus 36 equals 8x plus 48. Solving this equation will help us find the bounds of integration, or it will help us find where these two graphs intersect. So moving both of these terms to the left side. Gives us that quadratic equation to solve. And it solves for factoring x plus 6 times x minus 2. So x equals -6 and x equals +2. So those are the bounds of integration. Now, the way that you find the integral between two curves, or the area between two curves, is the integral from a to b of the difference of the two functions. Now, it's not always f of x minus g of x. It depends on which function is the upper function, like this straight line right here would form the upper region. We can assume, since it's a linear function going through a parabola, that the linear function would be the upper function. But you can't always just assume. So the best way is to check algebraically. So if you choose a value for x in this bound between -6 and +2 and plug it into each function, you can figure out which one has the higher value. That means that's the upper function in that region. So an easy number to plug in between -6 and +2 is 0. So if we check f of 0 and g of 0, f of 0 is going to be 36, whereas g of 0 is going to be 48. So the g function is actually the upper function, so I gotta switch this around. It's going to be g of x minus f of x. So it's going to be the integral from -6 to 2 of the g function minus the f function. You gotta subtract the entire function, each term. Alright, combining some like terms. 2x squared plus 12x. And since this is a definite integral, we evaluate the antiderivative at the upper bound and the lower bound and subtract. So this is the antiderivative evaluated at the upper bound of 2. So this is negative 8/3. And then 2 squared is 4. 4 times 2 is 8. And then plus 4. And then the antiderivative evaluated at the lower bound. Like a negative 6 and square, or cubic, right? You get 216, negative 216, and then it's already negative, so it becomes positive 216. And then negative 6 squared is 36, times negative 2, it's negative 72. And then 12 times negative 6. Negative 72. Let's see, I forgot that. There we go. So 216/3 is actually 72. 72 minus 72, those two cancel each other out. Minus a negative becomes plus. So this is plus 72 there. Negative 8 plus 24, that's 16. Okay, so let's see, 16 minus 8/3. 16 is the same as 48/3. So this becomes 40/3. And 72 plus 216/3. If we add those together, we get 256/3. Okay. Question 10 will be an integration by parts. So we want to let u equal something that when you take the derivative it becomes more simple, so it's going to be 2x. du is 2 dx. Now dv is something easy to integrate. E to negative 7x. dx is pretty easy to integrate. Big integral v is negative e to negative 7x over 7. So let's just check to make sure we have everything. This is u. That's dv. Remember the integral of u dv is equal to u times v minus the integral of v du. So we have u times v minus the integral of v. Now v has a negative 1/7, which you can pull out and have a plus 1/7 there. And then du has a 2 also. We're going to pull this 2 out. Right there. So we have e to negative 7x times dx. So it's negative 2x over 7e to 7x plus 2 7's multiplied. Now the integral of e to the negative 7x, we just did that here. It was negative e to the negative 7x over 7. We have negative 2x over 7e to the 7x minus plus c. And here we can try a u substitution. So we've got the x squared dx. We're missing 27, so we can place a 27 and then multiply by 127. So now we have 127, just an integral of du over u. Recall that's just the natural log. So this is 127 as a natural log of u, which is 9x to the third plus 5. Alright, question 12 is kind of a long process here. It's integration by parts twice, plus it's a definite integral. So first go around, we can let u equal x squared, which means that du is 2x dx. dv then is e to the 2x dx. When you integrate that, you get e to the 2x over 2. So expanding that integral, we're going to have u, which is x squared times v, minus the integral of v. Now v has a 1 over 2, so I'm going to pull out 1 over 2. And well, actually, du has a 2 and dv has a 1/2, so they just cancel each other out. The 1/2 and the 2. So we're going to have e to the 2x times x dx. And this is the part here that's going to require another u substitution. Or, another integration by parts. So we're going to have u is equal to x is du is dx. dv is e to the 2x dx. Which we've already done. The integral of that is e to the 2x over 2. So I'm going to rewrite the whole thing again, but I'm going to expand this integral using another integration by parts. So we're going to have x squared e to the 2x over 2 minus, and we have a u times v, so that's x e to the 2x over 2 minus the integral of v, which is e to the 2x, and we pull 1/2 out here. It's dx. So we're going to have x squared e to the 2x over 2 minus x e to the 2x over 2 minus, actually a negative times a negative will be a plus here, e to the 2x divided by 2, but then multiplied by the 1/2, so it's going to be over 4. So there's the antiderivative. It needs to be evaluated now between 0 and 1. So we need the antiderivative at the upper bound minus the antiderivative at the lower bound. So if we plug in a 1 right here, we're going to get 1 times e squared over 2, and then another 1 times e squared over 2. So e squared over 2 minus another e squared over 2. So those would actually cancel each other out, and we need to plug in a 1 here, so that would be e squared over 4. And then when we plug in a 0, 0 times that disappears. 0 times that is 0. So it's going to be e to the 0 power, which is 1, divided by 4. So the answer is e squared over 4 minus 1/4. Okay, here's another integration by parts. You have to be a little more careful about choosing u and dv. I think initially some students would look at x cubed and say, alright, that's our value of u. Problem is that would make dv natural log of x dx, and there is no integral for natural log of x, so we're going to have to place the natural log of x here. The derivative of that is just 1 over x dx, and the dv is x to the third dx, which means that v is x to the fourth over 4. So now the integral is going to be u times v, so that's x to the fourth times the natural log of x over 4 minus the integral of v. V has a 1/4 factor here, so you pull that 1/4 out, so that's x to the fourth, and then du is 1 over x dx, so that just changes into x to the third dx. Okay, so x to the fourth times the natural log of x over 4 minus x to the fourth over 16, and that needs to be evaluated from 1 to 4. So when we plug in 4, we're going to have 4 to the fourth power divided by 4 to the first power. That's 4 to the third power, which is 64, times the natural log of 4 minus 4 to the fourth power over 16, which is 16. When we plug in a 1, the natural log of 1 is 0, so that makes this term disappear. And then 1 to the fourth power is 1, so it's minus it's going to be 0 minus, so it's -1, 16. So we have 64 times the natural log of 4 minus 16 plus 1/16. So 16 is 256 sixteenths. So we have 1/16. We get 64 natural log of 4 minus 255 sixteenths. Question 14. This is going to have to be a partial fraction. So factor the denominator. Denominator has 2 factors, so it's going to have 2 partial fractions. We can multiply both sides by the LCD. And I have 3x plus 11 equals a times x plus 2 plus b times x minus 3. If we let x equal convenient values of -2 and +3, first go around with -2, you're going to have 5 equals -5e. Over here, you're going to have 20 equals 5a, so b is equal to -1, and a is equal to 4. So the original expression here could be separated into its partial fractions. So this becomes the integral of 4 over x minus 3 minus 1 over x plus 2 dx. So now you can take separate integrals. So integral of 4 over x minus 3 minus the integral of 1 over x plus 2. These are both natural log integrals. So this turns out to be 4 as a natural log x minus 3 minus the natural log of x plus 2 plus c. Okay, similar problem here. We have negative 3. Denominator would need to be factored into x minus 2 times x plus 1. Since the denominator has two factors, it's going to have two partial fractions. If you multiply both sides by the LCD, you're going to have a equals negative 3 equals a times x plus 1 plus b times x minus 2. Now using a convenient value of negative 1, and then over here convenient value of x equals 2. When x equals negative 1, we're going to have negative 3 equals negative 3b. So b is equal to 1. Over here, when x equals 2, we're going to have negative 3 equals 3a. So a equals negative 1. So the partial fractions are negative 1 over x minus 2 plus 1 over x plus 1. And we can integrate each partial fraction separately. And again, these are both natural log. So this is negative natural log of x minus 2 plus the natural log of x plus 1 plus c. Okay, improper integrals. These, if they converge, then the area under the curve can be found using a limit. So if the upper bound is infinite, then it's the limit as b approaches infinity of the integral from 1 to b rather than 1 to infinity. Now I'm going to go ahead and change this to x to the negative 3. The integral, or the antiderivative, is that. We need to evaluate the antiderivative from 1 to b. So this is going to be b to the negative 2, which I'm going to drop down to the denominator as b squared. So negative 1 over 2b squared. So I'm going to write this over here. We need the upper bound minus the lower bound. The upper bound is negative 1 over 2b squared. The lower bound here is going to be negative 1/2. So minus a negative is the same as plus. So there's the antiderivative. We have to take the limit as b approaches infinity. Now, we're plugging in larger and larger values for b as b is approaching infinity. So if you have negative 1 divided by an increasingly larger number, then this value becomes 0. And so we just have 1/2. So since the limit could be evaluated, it converges. And the area converges to 1/2. question 18. Will be the limit as b approaches infinity of the integral from 1 to b of x to the negative 1/5. So this is similar to before. We need to find the antiderivative of x to the negative 1/5. It's x to the 4/5 times 5/4. We need to evaluate that from 1 to b. So the upper bound, we're going to have 5/4 times b to the 4/5 minus 5/4. Well, when x is 1 to the 4/5 is just 1 times 5/4 is 5/4. So the limit as b approaches infinity of this expression here, 5/4 b to the 4/5 minus 5/4. As b gets larger and larger and larger, this whole piece of the expression continues to increase without bound. So this diverges. So now the lower bound is negative infinity, so this is the limit as a approaches negative infinity of the integral from a to 0 of e to the 2x dx. So the antiderivative is e to the 2x over 2, and we evaluate that from e to 0. So at the upper bound, plug in a 0, e to the 0 power is 1, that's 1/2. Lower bound is e to the 2a over 2. So we need the limit as a approaches negative infinity, 1/2 minus e to the 2a over 2. Now if we plug in values for a that are approaching negative infinity, that means the exponent of e is going to become more and more negative. Well, since it's a negative exponent, we can think about this as dropping down here, because it's going to have a negative exponent. Now, since we've dropped down to the denominator, the exponent becomes positive, and the exponent is increasing. So that means the denominator is increasing without bound, but the numerator stays 1. 1 over a very, very large, an increasingly larger number approaches 0. So the limit converges, or the improper integral converges to